Hi, and welcome to Lecture 8 for Psych 2317, Statistical Methods in Psychology. In this lecture, we're going to talk about how to construct confidence intervals for t-test designs, and you'll see exactly what I mean by that in just a second. So it's been a while since we've talked about confidence intervals. Let's recall what this is all about. So recall that we can estimate a 95% confidence interval for an unknown population mean mu simply using the sample mean and the population standard deviation by computing this. So we take x bar and then we say plus or minus this bit right here. This is called the margin of error. And we find that margin of error by taking 1.96 times sigma, that population standard deviation, divided by the square root of n. Now there will be a link to the lecture in which we talked about this in the notes below. Now equivalently, we could write that very simply to say x bar plus or minus 1.96 times the standard error. You may recognize that's what that formula is. Okay, so that's how we do confidence intervals. What if we are not given sigma? That's the big question now. We know that's an important question because when we're not given sigma, we have to estimate it from our data, and that's what led to the entire development of the t-test over the last couple of lectures. So I guess the question is, in this formula for the confidence interval, can we just use our estimate of sigma? Can we just use sigma hat, which we found, remember, as square root of SS over n minus 1? Why not, right? Well, I mean, mostly it's a good idea. So I'll say yes, sort of. But the big thing is we're going to have to adjust this 1.96 part. It's no longer going to be 1.96. What is it? Well, why are we going to have to do this? First of all, let's remember why we use 1.96. 1.96 comes about because for a normal distribution, it's easy to see that 95% of the sample means fall between negative 1.96 times the standard error and 1.96 times the standard error. Okay, so that number 1.96 was special because as z-scores, that held exactly 95% of the sample means. Now remember, using a normal distribution for this distribution of sample means assumes that you're given a value for sigma. But when you're not given a value for sigma, and you have to instead estimate it using this sigma hat, remember we no longer get a normal distribution, but instead we get a t-distribution for the sample means. And remember also that the exact shape of this distribution depends on the size of the sample. So what's going to happen here is this 1.96 that we've been using for confidence intervals is going to be different depending on how many participants were in the sample. So that's the purpose of today's lecture, is to figure out how to compute this confidence interval when it's no longer a fixed 1.96 times the standard error. So let's do that. So in light of all this discussion, we're going to define now what I might call a generalized confidence interval. So this is kind of a form that we'll always start with for our confidence intervals. We'll take our sample mean and then we'll say plus or minus this right here. This is t star df times the standard error. What is this t star df? Well, let's start there first. T star df is just going to be some number that depends on the sample size. What exactly it is this. It is defined as the value of t, which leaves 5% of the distribution in the two tails combined. So in other words, it's how far you have to go out from 0 on the t-distribution to encapsulate 95% of the sample means t-scores. Okay, so sometimes this is called the critical value of the t-distribution. You'll see that in books. And I will say that I'll show you very soon, it's easy to find this value from our distribution calculator app that we've been using, and the link is down below. Okay, so that's t star df. What about the standard error? Well, the formula for the standard error is going to depend on our design. So if we're using a single sample, so the things that we started with this semester with t-test, or even repeated measures, then we have a very simple formula for the standard error. It's just sigma hat over the square root of n. Okay? But If we have, like in the last lecture where we had 2 independent samples, then we have a slightly more complicated formula for the standard error, and we introduced this formula last time, and it's sigma hat p, the pooled standard deviation, times the square root of 1 over n1 plus 1 over n2. So to solve any problem here, that is to find a confidence interval, we're going to have to find 2 things. We're going to have to find t star df, okay, and we'll find this from our app, and then we're going to have to find the standard error, and the formula for that standard error will either be this one if it's a single sample, or this one if it's 2 independent samples. So let's do an example of each of those just to see this in action. So we'll start with the simplest one. We'll start with a single sample design, and here's a little problem. We've got a sample of 25 people that are given a treatment, and after treatment we find sample mean of 22.2 with SS equal 384. And I want to construct a 95% confidence interval for mu, which is the population mean of the treatment group. And just to be real clear, that's not mu1, that's mu comma. Okay. So how do we do this? Well, let's get started. First of all, we're going to start with that generalized form for the confidence interval. That is, we're going to start with x bar plus or minus t star df times the standard error. Okay. Now we're going to work on each of these pieces, and once we have them all together, we can put it together and very simply write out our confidence interval. Well, the first thing we want to find is t star df. Okay. Now in this problem, what is df? df is 24, because remember the degrees of freedom is 1 less than the sample size on a single sample design. It's just n minus 1. So df is 24. So from the app, we're going to go find t star df. I'm going to show you how to do that real quick. So let's go to our app. Again, the link is down below. And remember, the app starts just like this. It assumes you've got a normal distribution. Since we're dealing with a situation in which you would use t-scores, that is, we're not given the population standard deviation, we need to switch to the t-distribution. Now, I said that the critical value for t, this t star df, is given to you. It's not written out, though. It just kind of pops up, and here's how you do it. Put in our degrees of freedom. Our degrees of freedom that we just figured out for this problem was 24. Now, if we will go and select both tails, you'll notice that 2 numbers pop up in the A and B slots here. And it turns out that these 2 numbers are almost exactly, at least to 2 decimal places, what we need to get 5% in the tails, that is this p-value. Those 2 numbers are, well, 2.06 and negative 2.06. So by a simple little clever thing in the program, we get the critical value given to us right there in that A and B box. Our t star df is 2.06. You'll notice if I put in a different value for degrees of freedom, let's put in, I don't know, 15, okay, and then select both tails, you'll notice this changes responsively to a different number, but it changes to a number that fixes this p-value to be 5%. All right, so that's how you find your t star df. That's how you find your critical t-score. You put in the degrees of freedom, select both tails, and then it pops out in A and B automatically. So it's 2.06. So let's go over here and write this down. T star for 24 degrees of freedom is 2.06. Okay, so we've got that. Again, just go to the app to find that t star, that critical value for t. Now we've got the t star df. We need to find the standard error. Now this is a single sample design. So the formula for the standard error, we look back and it's sigma hat over the square root of n. Okay, well, what is sigma hat? Well, we need to go back and remember that to estimate sigma hat, we need to compute the square root of SS over n minus 1. Now we were given SS as 384, so we take the square root of 384 over 25 minus 1, which if we work this out and simplify, it becomes a square root of 16, which is simply 4. It's a nice little example here. So that's sigma hat. What is the standard error? Well, the standard error, we take sigma hat over square root of n, so it's 4 over square root of 25, which is 4/5, which is 0.8. So we've got, our sample mean was given to us in the problem, we've got t star df, it's 2.06, and we've got the standard error, it's 0.8. So let's put all this together. Putting this all together, our 95% confidence interval will be sample mean of 22.2 plus or minus T star DF times the standard error. And let's go ahead and figure out what this margin of error is. Remember, you need to do that multiplication first. So that becomes, oops, that's not what I wanted to do. That becomes 22.2 plus or minus 1.648. So when I multiply those two together, that's what that becomes. And so this means I take 22.2 minus 1.648, and that gives me 20.55 on the lower end. And then I take 22.2 plus 1.648 to get 23.85 on the upper end. So our 95% confidence interval is between 20.55 and 23.85, so we are 95% confident that mu, that population mean, lies in between these two numbers. And that's how you do a 95% confidence interval, at least for a single sample design. Now, what about an independent groups design? Well, it's a little bit different because in an independent groups design, we have two population means. So our goal here is going to be not to estimate the means themselves, but to estimate the difference in those means. We'll just call this the mean difference, mu1 minus mu2. Think of it as the effect or the raw effect of moving from one group to the other. So the resulting formula for that CI is very similar to what we've already seen. It's instead, though, we have two sample means. So we're going to take the difference in those sample means, and then we'll just say plus or minus T star DF times the standard error. But this time, the standard error is given to us as this guy. Okay. So let's work out one more problem and see how things change here. Not much really changes, just some of the specific calculations. Okay, so here's our second example. And so we're going to ask, does watching educational TV as a kid predict better high school grades? And so we've got some summary statistics for a group of kids who watched educational TV and a group of kids who did not watch educational TV. You can see that the mean of the educational TV group is a little bit bigger than the mean for the no educational TV group, and their variability roughly the same as indexed by the sum of squares. So our goal here is to compute a 95% confidence interval for the mean difference, mu1 minus mu2, where mu1 is the population mean of this first group, educational TV, and mu2 is the population mean of this group. Okay. So let's do that. Let's do this solution. So first thing that we'll do is write out the form of the 95% confidence interval. And since it's two groups, I'm going to write it as x1 bar minus x2 bar plus or minus this thing that should be familiar to us now, T star DF times the standard error. So let's take those two pieces of information. What's T star DF? Well, we need to know what the degrees of freedom are. DF, remember, is the sum of the degrees of freedom from the two groups. Since there were 10 in each group, that sum becomes 9 plus 9, one less for each group, which gives us a total degrees of freedom of 18. So what we need is T star DF for 18 degrees of freedom. So let's go back to our calculator. We'll put in 18 for the degrees of freedom. And we can see for both tails, we get critical values here of 2.1. It's 2.10 is actually what it turns out to be. So we'll write that down here. 2.10. Okay. All right, so now we've got that. What's next? Well, let's see. We need to find the standard error. Now remember, for two independent samples, the formula for the standard error is sigma hat p times the square root. So that means we need to find sigma hat p. Now remember from the previous lecture, lecture 7, I believe, we take the square root of ss1 plus ss2 over df1 plus df2. Filling in what we have, we were given that ss1 was 200 and ss2 was 160. And we'll divide by df1 plus df2, which is 9 plus 9. That gives us a square root of 360 on top over 18 on bottom, which simplifies to the square root of 20, which if we put that into a calculator and take two decimal places, we get about 4.47. So that's our pooled estimate for the standard deviation. Now we can use that and feed it into the formula for standard error. We take sigma hat p times square root of 1 over n1 plus 1 over n2. So that's 4.47 times square root of 1 over 10 plus 1 over 10, which if you put all that into your calculator and do the order of operations correctly, you get to 2 decimal places, 2.00. Okay. So we've got the means. Those were given to us above. In fact, we should go back and look at what those were. Those were 93 and 85. We've got T star DF, which turned out to be 2.10. And we've got the standard error, which turned out to be 2. So let's put it all together. So the form for the 95% confidence interval, one more time, is this, the difference in the sample means plus or minus this margin of error. So the means themselves were 93 and 85. So the difference between those will be 8. And then T star DF was 2.10. Standard error was 2. So we need to multiply these two together. So that gives us a difference of 8 plus or minus 4.2. That's what this product turns out to be. So we'll take 8 minus 4.2 and 8 plus 4.2 to get an interval of 3.8 to 12.2. So we are 95% confident that the difference in these groups at the population level is between 3.8 and 12.2. We can sort of use that as a de facto hypothesis test. We can say we're 95% confident that that difference is not 0. And so we can conclude there is a significant difference between those two groups. And that's how this is often used in a hypothesis testing situation. I prefer to just do the hypothesis test, but they do give you roughly equivalent results. So that's it. The big goal today is how do you compute confidence intervals when you don't know sigma? And the answer is, well, it's not too bad. You just have to figure out what this number is. It was 1.96 always. Now it's something different depending on how many, what your sample size is and what your design is. But these are the two main things that you can do. So that really, that gets us a long way. And we've got a nice app to compute this critical value, so we can do that. So that's all for now, and we'll see you on the next lecture.